All right, I'm going to briefly talk through each of the 10 questions that were on the Chapter 19 Extra Credit quiz in class today. First one's pretty simple. I just want you to find the cell potential, in other words, E cell. And it was even nice enough to show you what the overall reaction is. But you need to know which of these two half reactions to reverse, because then if you reverse the reaction, you have to reverse the sign. And so this reduction magnesium had a minus 2.37 volt. And so we're switching it to be the oxidation. And so just so that you can look at the overall reaction, once we flip the magnesium one, and the electrons cancel out. All right. And so since we flipped this one, we've got to change the sign to positive, which I did. When you add those together, you get overall cell voltage of 2.71. All right, so this one is, and the most challenging part is going to be knowing which formula to use. Just a reminder, I will give you all of the formulas on the test. All right, so you have to know to use the Nernst equation. That's the equation for calculating E cells under non-standard conditions. And you need to be able to identify the non-standard conditions. Although temperature is standard, concentrations are not. Standard concentrations are 1 molar. And so you have to use the Nernst equation. You have to find the standard cell potential first. So I did that. All right, here. Okay. And of course, as always, you have to flip one of the half reactions to make it an oxidation. And the more negative one is the one that makes more sense to flip, and so this becomes a positive 2.37, and therefore the standard cell voltage is 1.92. So if I go and plug into the Nernst equation, standard cell potential of 1.92, and then 0.0592 divided by 2, and then log of magnesium over iron. Okay, let's see what that gives us. And our answer for this one is 1.9 volts. So also you should be able to identify, if you compare the two voltages, it was 1.92 originally. And then when the concentrations were changed, it went to 1.90. So you can see it didn't change very much. And of course the change depends on this part of the formula. Okay, so this reaction, this was my hint, it's unbalanced. So, and you can tell that right away. I mean, there aren't oxygens on the product side. Yeah, you can just tell right away. So if a reaction isn't balanced, then make sure you balance it first. And I think some of you, temporarily forgot how to balance. You have to find the two half reactions yet. And I started out with a manganese pair. And then you go to the iodine pair. And then, of course, keep in mind what the question is asking. It's just asking how many electrons are transferred. So as soon as you get the electrons to match, there's your answer. There are 10 electrons that have been transferred in this reaction. All right, anode, oxidation occurs. An ox chased a red cat. So at the anode will always be oxidation. So now we have to figure out which of these two half reactions undergoes oxidation. The one you flip is the one that undergoes oxidation. So we would have to flip this one because it's the more negative. Okay, and then when you want to see the overall reaction that's occurring, it's right here. And you can see that it's actually the neutral chromium metal that is getting oxidized with the chromium +3 solution. And so I think the question said touch where it is. So this is the actual electrode, right? Not above it or below it. Now, this question, one of the choices was kind of confusing, so I gave a few more people credit than probably expected. All right, so again, the first thing that you should always do, even if they're not asking you for balanced reaction, is you want to figure out a balanced reaction, and that's by combining the two half reactions. Of course, we would flip the aluminum one and get its standard cell of plus 1.66. And this question says, mark all the following statements that are true. So once you have the reaction written as it occurs, you can see what is reduced. Okay, and you can see that it is Pb2 plus is the one that's reduced. And you can also see that what is oxidized is the aluminum metal. All right, so clearly the lead cation is reduced. It is not okay to just say, well, can't I just say lead's reduced? No. Neutral lead is not the same thing as lead cation. So you have to pick exactly the reactant that's reduced or oxidized. And by the way, the only thing that can be reduced or oxidized are the reactants. The products are what is formed. So anyway, so A is circled, and then looking at all the possibilities, aluminum is oxidized because remember it goes to aluminum +3. And the cell potential, if you flip the right one, is 1.53. And electrons always flow from the anode to the cathode. Oxidation occurs at the anode. So the electrons flow from aluminum to lead. Aluminum is the anode, lead is the cathode. This positive and negative stuff, I'm going to give you credit whether or not you picked either one of these. There's so much controversy over what you call positive and negative, because there's two different ways to look at it that I'm not going to even ask you that on the test. Okay, and then finally the salt bridge one. Anions go to the anode, cations go to the cathode. All right, so this is simply calculating equilibrium constant from cell, E cell. So you need this equation. And let's see, I was trying to think of what people mostly missed. So you need the standard cell potential. This problem gave it to you. The same exact problem was on one of your quizzes before too. But so here's the standard cell potential. Number of electrons transferred is, for this reaction, is 2. And then you just solve for K. I guess the only thing that might trip some of you up is the math. So the first thing you want to do is divide both sides by 0.0296. Okay, which gives you this. And then remember, to get rid of logs, you raise both sides as an exponent to base 10. And the base 10 and the log cancel each other out. So you end up with K, the equilibrium constant, equals 10 raised to the 0.473. That's 2.97, and when you round it, it's 3.0. This problem is one of the giant unit cancellation ones, and I think probably the most important thing for you to remember is that an amp, okay, an amp is coulombs per second. And you have to remember that because coulombs per second will set you up for canceling units. You can do this in almost any order. You could have dealt with coulombs first or time first. I chose to deal with time. 180 minutes was given, so I knew I needed to convert seconds into minutes. And so when I did that, I ended up with an intermediate value of 108 coulombs, 108,000 coulombs. And then, of course, Faraday's constant, capital F. But anyway, take a look at this. You do need to be able to do these. Will very likely be one of your free response questions. This question surprised me. Almost nobody got it right. So the correct answer was A. In order to know whether or not a reaction is an oxidation-reduction reaction, you have to assign oxidation numbers. And a lot of people are forgetting to use oxidation numbers. You can see anytime you have a combination reaction, actually it's going to be a oxidation reduction, because elements in their standard state have oxidation numbers of 0, and then of course anytime they form a compound, they don't have an oxidation number of 0. So anyway, the correct answer is A. However, I am also going to give credit for C because this subscript 3 was left out. So this should actually read AGNO3. And so I'm going to go ahead and give credit for people who answered C. But one thing I want you to remember here is double replacement reactions are never redox reactions. Never oxidation reduction reactions, ever. So if you wanted to prove it to yourself, this is a double replacement, this is a double replacement. You could assign oxidation numbers and see they don't change from one side to the other. Okay, so this reaction, as all redox reactions, in order to balance them, you need to break them into half reactions and carefully balance each half reaction. You end up having to multiply this half reaction by 3 in order to get the electrons to be equal. And so you end up with this on the bottom. You're probably pretty rusty on balancing redox reactions, the first thing we did, so you definitely will probably want to go back to that worksheet and get some practice. Okay, so the coefficients that end up needing, oops, I left my hydrogen ions out. This side has 14 hydrogen ions, and this side, after I multiply by 3, has 6 hydrogen ions. Okay, so when I combine those, I end up with 8 hydrogen ions over here. So the coefficients that work are, let's see, 3, 1, 8, 3, 2, 7, I hope. Okay. This is probably the trickiest type of problem. This is an electrolytic cell. Okay, that means a non-spontaneous one, and it's also done in water. Notice it's in aqueous solution, AQ. So this is the type of problem where that gets tricky, because not only can the substance itself be oxidized and reduced, magnesium iodide, but since it's in water, water is a competing substance to get oxidized and or reduced. Man, I was really sloppy on this page. It's late. Sorry, guys. I'm tired. And so what I suggest to do is make 2 columns, one oxidized, one reduced, and there are 2 possibilities under each column. So one of the things that can get oxidized are the anion, whatever that is, in the initial salt, and it happens to be iodide for this one. So write that out as a possibility. Look up its voltage in a standard reduction table. It's 0.53 volts. Or the second possibility of something that can get oxidized is water. And Water being oxidized has a standard cell potential of 0.4. So which of these two is going to get oxidized in this cell? It's going to be the one that is more positive. And so the iodide is the one that'll get oxidized. So oxidation occurs, I just realized that's not even what they're asking. Oxidation occurs at the anode, and the question is saying what reaction occurs at the cathode. So we need to find reduction. And so you do the same thing for reduction. So the two possibilities for reduction are the cation, which in this case is magnesium cation, which has a standard cell potential of 2.37 volts, minus 2.37 volts. And water's reduction potential is minus 0.83. So which one of these is more likely to, or is going to be reduced? And again, it's the one that is most favorable, most positive, or in this case, least negative. Reducing magnesium takes a lot of energy, so definitely water is going to get reduced in this one. You got to make sure you have the right equation for water. As we noticed the other day, there are 2 or 3 different half reactions involving water. Make sure you get the one that is actually reduction in this case. So, I don't have it on the page anymore, but it would just be showing water getting reduced here. That's it for the quiz. I will see you on Monday for your last test. And remember, it's over thermo and electrochemistry, chapters 18 and 19. And that's it for now.